The last session I had discussed about the location and the direction of the cracks in the cast products. So, how the defects will look like, whether on the surface or internal, I had mentioned about those. So, there are two basic categories. One of the surface crack, which you can see on the surface itself of the cast product, whether it is bloom or billet or round or slab. So, there may be longitudinal cracks in the direction of the casting, which is called longitudinal, at mid face or near corner locations or any random locations, and for a round section it can be all around, that means it does not have any specific location, but it is a round section. But for billet, bloom and slab, it can be near the corner, it can be off corner, it can be mid face, or it can be any other location, specific locations. So, mainly they coincide with a longitudinal depression. Without depression also there might be cracks if there are some severe casting problem during the process of continuous casting, then also there can be cracks without having any depression. But normally you have surface cracks coinciding with longitudinal depression, or you might have cracks, you might have depression, but the cracks will be at the subsurface location. I showed one example in the last session. Now there can be transverse cracks also. This I am talking of longitudinal cracks, surface cracks. Then there can be transverse cracks primarily related to either deep oscillation marks or transverse depressions. And I have mentioned that normal oscillation marks, which are not deep, which are shallow, they do not constitute any defect. They are normal surface, some manifestation of oscillation on the surface. But if they are deep, if the oscillation marks are deep, then it is a matter of concern. You have to be careful about avoiding deep oscillation marks. So, if you have deep oscillation marks, then sometimes beneath those deep oscillation marks there can be transverse cracks, and if there are transverse depressions, there also can be transverse cracks just below those depressions. So, at the surface there can be different defects, there can be different quality issues. Similarly, there can be internal defects or internal cracks or segregation, which you cannot see with your normal eye because it is not on the surface, but either it is subsurface or at different depth, maybe subsurface, maybe at the mid area, that means called the central area, or maybe in between the central area and the surface. So, it can be anywhere. So, as I was telling, if it is midway, midway means at the in between the surface and the central region. It can be the diagonal areas, that means when the two solidification fronts are matching, those areas that interface between the two solidification fronts is a weak point, weak area, weak joint. So, there might be cracks. At the triple point, again three solidification fronts are meeting at triple point from the two broad surfaces, top and below, and also from the one narrow surface. So, all the three solidification fronts are meeting, so at triple point. So, that is again a weak area, weak joint. So, there might be some cracks, and of course, there might be cracks or segregation at the center line. I have mentioned how this can be controlled, center line defects, segregation, or cracks, shrinkage cracks, or too much of porosities can be controlled to some extent by using mechanical soft reduction. I had also mentioned it has to be of certain intensity, the intensity of the reduction, and also the location where you put the reduction, that is very important. It cannot be just anywhere, it has to be near the end of solidification zone, final solidification when it is taking place. In that area only you have to put pressure, some soft reduction, some reduction in thickness, through that only you are applying pressure, and it is not sudden, slowly in steps you are increasing. There is a gradient of pressure development at the final solidification front. In that process you can reduce the intensity of defect at the center line, whether it is cracks or whether it is prominent segregation, pronounced segregation at the center line. So, and then I had mentioned how the different cracks look like at the surface. There is billet, bloom and round, longitudinal, it can be mid face. Then I have talked about internal defects in billet, bloom and round, how do they look like, and you have to cut an cross section. So, you have to see only at the cross section. On the surface you do not see anything. These are internal defects. Surface is absolutely free, but if you look at the interface cross section, then only you will find some defects if they are present. It can be diagonal, it can be at the mid area, it can be near the corner, it can be this is corner, this is off corner, and this is spider of different orientation. So, similarly on the cast slab also you may have on the surface lots of cracks and different orientations, longitudinal, mid face, near the corner, at the corner, and transverse at the corner, all sorts of this is fine cracks without having any typical orientation, but maybe small cracks located at certain areas. So, again in the slab interior, the internal cracks you might see, this is a center line crack or segregation, this is a triple point, this is a triple point, solidification front moving from here, solidification moving from the broad faces, meeting at the triple point area. So, this area is very weak, so you might have crack development at those triple point areas. Then this is off corner longitudinal, you are looking only at the trace on the section, you are looking only at the trace of the crack. Then again it can be transverse crack near the surface, transverse crack near the center. So, all sorts of cracks I have talked about. I have talked about the scheme for mechanical soft reduction to control defect at the center line. I have mentioned two important issues here, where you put the pressure and how much pressure you put. This is very important. Where you put the pressure near the solidification completion zone, and if you put less pressure it will have no effect. If you put more pressure there might be formation of internal cracks. So, the intensity of reduction, intensity of pressure has to be somewhat optimum. So, this is again important issue. Then how with mechanical soft reduction the intensity of central defect, central crack or central segregation is coming down. This is just to show. Then I talked about in 304 is a typical so called peritectic grade in stainless family. So, under the depression, longitudinal depression, you might have surface crack. On the surface you are seeing only depression, but if you take a cross sectional view you will find trace of subsurface crack. So, how it can be taken care of? By minor adjustment of chemistry. How? By taking a nickel equivalent of chromium equivalent slightly less than the peritectic start chemistry, which is 0.55. So, if your nickel equivalent by chromium equivalent is say 0.54, 0.53, 0.52, the incidence of depression is much less compared to the situation when this nickel equivalent by chromium equivalent is more than 0.55, which is about say 0.58, 0.57, 0.56. So, by minor adjustment of chemistry, of course, within the range of specification of AISI 304, it is possible to control the incidence of depression to a large extent, keeping the parameters more or less, casting parameters like mold taper more or less similar. Then I have mentioned for a austenitic solidification situation like AISI 310S, which is a totally austenitic grade at all temperatures. At start of solidification it is austenite, during solidification it is austenite, after solidification it is austenite and continues to be austenite. In such grades microsegregation is relatively more because of austenitic solidification. So, here the issue is to control of phosphorus and sulfur assumes much importance. The phosphorus and sulfur have to be controlled to to reduce the incidence of intercolumnar cracks in slab. These intercolumnar cracks you always do not see on the surface, it is internal locations at intercolumnar locations. When these cracks in slab will finally result in the rolled product, we call it surface tears, that means surface cracks on hot rolled plate or hot rolled coil or sheet. So we have to be careful about the intercolumnar cracks, and the solution lies in controlling phosphorus plus sulfur. So now today I will talk about when we understand what is the solidification characteristics, whether it is a ferritic solidification or austenitic solidification, whether it is characteristic is sticking type or bulging type on the one hand, or it can be depression type on the other hand. Then what do you do? What is the way out? When you know the mode of solidification, when you know the solidification characteristics, then we know, I have told you, we can adjust the casting parameters accordingly, so that the solidification quality, that means the quality of the cast product, is relatively better. If you understand how the solidification is taking place, whether it is through delta or it is through gamma, or when the delta to gamma is taking place, this transformation, the at what temperature is taking place, at what stage is taking place, is it taking place at the start of the solidification or towards the end of the solidification, which is very crucial, which is very critical. So we have to be careful about that, or it is taking place after solidification, like when you have a ferritic grade like very low carbon or a silicon steel, is a very much ferritic solidification. You have to delta solidification, delta ferrite solidification, and delta to gamma takes place only at much lower temperature. So there what are the issues? Number one, when you have a so called peritectic grade, then what are the issues? Issues there is, it is taking place through initial solidification is taking place through delta, but delta to gamma is taking place, transformation is taking place towards the end of solidification, which is a brittle temperature region. So that has certain defects. Surface you have lot of depressions, you may have crack because of that. So it is a depression prone grade. Then you might have a chemistry like very high carbon, say more than 0.3, 0.35 or more than 0.5, or in stainless steel family a grade like 310 or 310S, which is totally austenitic solidification. There what happens? During solidification the shell is thin because of pronounced microsegregation of phosphorus, sulfur and other elements. So here if you understand how the solidification is taking place, whether it is a depression prone grade or sticking or bulging prone grade, accordingly we have to decide the casting parameters. So first let us talking of this grade specific selection of casting parameters. How do you do? Like I have mentioned, for the sticking grades, the important parameter there is lubrication. It has to have better lubrication in the mold, so that the sticking situation can be taken care of, so that the friction owing to sticking does not go beyond a certain value, critical value. So their lubrication has to be better for the sticking grades. So accordingly the mold slag has to be suitably selected. The characteristics of the mold slag should be such that it has better lubrication, so that the sticking tendency can be controlled. If there is too much of sticking, there might be sticking breakout, the surface may be ruptured, so all sorts of problems will be there. So if you understand the solidification characteristics, we know that it is a sticking grade for say very low carbon or ferritic grades like 430 or maybe silicon steel. These are all very prone to sticking, and beneath the mold, below the mold, it will indicate bulging. So there also something has to be done. As I mentioned, secondary cooling has to be high to control bulging in very low carbon and ferritic grades, silicon steel which is a ferritic grade, ferritic stainless steel 430. So, their secondary cooling intensity, what should be the distribution, these will play a very important role, and the mold slag has to be such that you get better lubrication. But for a peritectic grade like say 0.1% carbon, or in the stainless steel family 304 grade, which indicates depression. So, it is a grade which shows a lot of surface depression. So, what you have to do? Why there are a lot of surface depression? Because this delta to gamma transformation taking place at the crucial brittle zone of between LIT and solidification completion. That means between the solidification zone of 90% and 100%, when the solid fraction is between 90% and 100%. If the delta to gamma transformation takes place in that area, which is a brittle temperature zone, you have additional shrinkage, that means additional strain. So, there is a possibility of crack formation, depression formation. So, what do you do for such grades? For such grades, you control the heat transferred in the mold, because everything is taking place in the mold. Surface solidification is taking place, subsurface solidification is taking place in the mold. Maybe about 10, 12 or 15 millimeter is already cast in the mold. So, whatever control you have to do a control in the mold by using mold slag which has characteristics of low heat transfer. Mold slag should be such that the heat transfer is low and it is uniform throughout the periphery of the mold. That means addition of powder is very important. You should always have a uniform powder addition throughout the periphery of the mold. Sometimes certain areas, certain localized areas of the mold might have higher amount of powder, or might have lesser amount of powder, and because of that heat transfer near the periphery, near the meniscus in the mold gets affected. So, first it has to be uniform powder distribution, uniform feeding of powder from the top, and also the powder characteristic should be such that we have lower heat transfer, we have uniform heat transfer, and therefore, we have less of depression in these peritectic grades. So, first depending on understanding the solidification characteristics, understanding whether it is a sticking and bulging or depression grade, we have to select the casting parameters accordingly. Then I have talked about base chemistry. What should be the optimum base chemistry within specification? This is very important. All steel grades have a specification which is designed based on the application requirement, but there is a range for all the alloying elements. So, within the specification range it is always possible to do minor adjustment of chemistry, and I have given you an example how minor adjustment of chemistry can give much better quality. I have talked about AISI 304 stainless steel, where normally the 304 chemistry gives a nickel equivalent where chromium equivalent is around 0.57. I am talking of the normal which people use, but the range of chemistry is such that with minor adjustment you are still in 304. So, what can be done? Because this 0.55 is the start of the peritectic temperature, a peritectic reaction in the stainless steel family, which is at 0.55 nickel equivalent by chromium equivalent. I have discussed this earlier. So, if you can adjust the nickel equivalent by chromium equivalent slightly lower value, say 0.54, 0.53, 0.52, then you can get much less depression. Why this is happening? Because this I have talked about you, there is a delta to gamma transformation for this types of chemistry, whether it is around 0.1 or around 304 stainless steel, 0.1% carbon grade or ASA 304 stainless steel. It takes place around the solidification completion temperature, and I have told you that solidification end region, say from 0.9% solidus rather 0.9 solid fraction to complete solidification. That means when the solid fraction is 90% to 100%, that area is very prone to depression formation, because it is a brittle temperature area. It is a temperature area between LIT and ZDT. That means when the ductility of the, or the the reduction in area of the strand solid shell is very low, almost 0, and then if you have shrinkage due to transformation of delta to gamma, that creates crack formation and depression. So, what we are doing, we are slightly adjusting the chemistry to bring it lower than the peritectic start temperature. So, what is the issue here? Delta to gamma will take place lower than solidification, at temperature which is lower than solidification completion, not around solidification completion. So, with minor adjustment we can, you see, we can get very low incidence of this depression in this depression prone grade of 304 stainless steel, or so called 0.1% carbon, which is a peritectic, which is known as a peritectic chemistry. And then I have also mentioned about 310S, it is a totally austenitic solidification grade. So, here what happens, due to total austenitic solidification, the role of microsegregation is very pronounced, and because of that the shell is very thin, and because of that the shell cannot withstand ferrostatic pressure. So, you have lot of intercolumnar, you might have lot of intercolumnar cracks, that those area is having low strength. Intercolumnar areas are very rich in segregating elements like phosphorus, sulfur, and their incipient fusion problem is there, their solidification temperature also comes down. So, these intercolumnar cracks, incidence of these cracks is very high in a grade like 310S, which is austenitic solidification grade. It is similar to very high carbon grades like 0.5, 0.6, 0.7 ball bearing steel. All these grades you have this problem of intercolumnar cracks. So, we have to be careful. How we can be careful? The only success can be if you reduce the phosphorus and sulfur content, then the incidence of segregation will be less, and then intercolumnar areas will be relatively less sensitive to crack formation. So, the incidence of cracks are less, and if the incidence of cracks are less, then when you roll it, the surface of the rolled product also will indicate less surface tear, less surface cracks. So, here the internal cracks is the main issue. So, if you understand what is the solidification characteristics, accordingly we can devise the solution route, what should be the way out, how to take care of the problem. So, for austenity grades of solidification I have mentioned, phosphorus and sulfur is very important, manganese by sulfur ratio is very important. So, that is precisely what we have to do